Okay, Tina Koto Katoa. So it's my pleasure to introduce our recent work that we are currently doing. My name is Yimei from the same school. Actually, we will have a bunch of people from the same place presenting today. So my research is mainly about AI and machine learning for planning, scheduling, and combinatorial optimization. And we have worked on many problems in the real world, and today I'm going to introduce a recent problem that we are working on, which is ambulance dispatching that we're working on. So ambulance dispatching, I'm not sure how have you experienced calling for an ambulance, and this is I don't have much experience before, but one of my students actually had a really bad experience. So that's why he actually came and said, okay, we would like to improve. So we can see the ambulance dispatching is a really hard problem, dispatching, and we have a lot of dynamic environment. We have new calls coming in real time, and also we don't really know how the patient is doing at the moment that we receive the call, and also a lot of interactions with the ambulance, and it's a really hard dispatching problem. And just an illustration of this, we have some ambulance, we have the calls, ambulance serving the calls, and maybe we have some new calls when we are really doing the job, and hopefully we get some idle ambulance when we receive the call, and that's what we are trying to do, how to decide which ambulance and go to serve which course, depending on a lot of complex factors. And we can model this as the Markov decision process. Basically, we have the states, how the ambulance and course look like, the road network, the traffic, and what's the action. Basically, given that we are, what currently has been allocated and what we are trying to do based on the new course and how the ambulance look like. So this, and we also have the reward, mainly considering how fast we respond to the patients. Of course, we want to respond as fast as possible. So we mainly categorize the decisions in this problem in when we have new emergencies coming, or we have a new ambulance idle. They finish their current job, and there are also a lot of more concrete decisions in this case, but we simplify the problem because this is some initial preliminary studies, and we mainly focus on this, how to dispatch the ambulance when they finish their job, because usually it's busy and we have to wait for the ambulance to really finish their current job and to get to the new one. So we use machine learning, or more specifically genetic programming that Chi just mentioned. We use that to learn the rules. So for the EMD rule, given a state, and we want to apply this rule to actually come up with the decision, which is to dispatch the ambulance to the emergency. And how can we represent? We use a priority function or scoring function to represent the rule. Basically, given an ambulance, and we can have a bunch of emergencies waiting in different places, different urgencies, and we basically consider the pairs, and we use the rule to calculate the priority or the score, and then we select the best one, which is we think the most urgent or prioritized one. And to learn the best rule that makes the best decision, we can represent the rule as a tree, and we use a bunch of attributes or features representing the current state, and we can use a tree as a combination to calculate the priority. And then we are basically searching for the best rule in the whole rule space. So given the training data which we can get from the historical data, and we have the rule, how do we evaluate this rule? First, we get this simulation, or we get this simulation, and we use the data to initialize the environment and also simulate the arrival of the emergencies, and we simulate how we can make the decision by the rule, and finally we get a solution to calculate the fitness or how good it is. And then we use the GPU to learn. So I'm going to skip this because it has already been introduced. And we apply it to some data sets, small, medium, or large data sets. We have the number of cores from 75 to over 300, and also small to large road network. And we found out that we actually can learn the rule that make over 50% improvement, in terms of the response time. So yeah, that's what we have been doing. Of course, there are a lot of other things to do. The interactions between different vehicles or ambulances, and how to coordinate between the different vehicles and different types of the patients, and also how to apply to more complex and real data. And this work is not just by myself, and also like to thank my group members, Fang Fang and Mong there, and they're all here. And also thank you for my group members. So, thank you.